We should be both then recording and screen sharing. So welcome. This is our official final get together. This is it. This is the end. Um, I think I said this before we got started that this should be a celebration. So I know you're all many to various degrees tired, exhausted, stressed, worn out, over it. Let's treat this as a celebration. Every team that I can see made a lot of progress, got a lot of cool things working. Nobody got it perfect. So we're all at a place where you made good progress. Some compromises here or there, running out of time. I understand all those things, but I'm really impressed with what I've seen so far, and I'm looking forward to seeing your take on it as well. Um, as we get started here, just a little bit of our logistics of how this is going to go. We started here at 9:45. I do want to stand at 11:45. If it's 11:46 or 11:47, that's fine. So I do want us to try to just stay on top of our time here. I will be um, interrupting you for the most part, other than a question or two, just to say, "Hey, we have to go," or "Hey, get to your final slide, and we have to be done." And that's okay too. People can also read the slides. Oftentimes, for a typical presentation, you can just read what the information was versus having to hear someone say it. We're going to say it as well. It looks like most of the teams did, to some extent or another, follow the template, so we're doing that. And I want everyone to have a separate tab open for that Qualtrics survey. So we will take that 2 to 3 minute timeout after every presentation. And I believe I've set it up correctly. Um, Qualtrics does this thing where if you've gone to the survey and you're using the same IP address, it'll return to where you were. But I have edited the survey, so if you are seeing an old version of the survey, you may need to do exactly what I did right now. I opened up an incognito window so that it just got rid of its memory of what survey was in the browser cache. I don't know entirely what happened, but in any case, um, you get a fresh version of the survey, put your net ID in there, get ready. Actually, you'll want to go to team two. We're doing the evens first, then the odds, but you're going to be able to skip around and go back and forth. So I think it's self explanatory, but let me just very quickly walk through what I meant by this. So this is literally just a copy paste of the rubric. It should match exactly what is on the slide that the teams will be going through at the very end of their presentation today. This is just a sliding scale for the attributes in the rubric. Um, I tried to be faithful to how you set up your rubrics. Qualtrics was a little limiting. Some did left to right, where left is bad and right is good. Others did right to left. Either's fine, but the sliding scale I have matches that. So you'll see some that go left to right and others that go right to left. Also, I did the scale of minimum amount of points. Well, zero I put as minimum, and then 75 if that's what group two put here, even though not all their attributes are. So this doesn't do a summation for you, but try to keep to what it's saying here. So for example, while the sliding scale says up to 30 for get integration for group two, don't give them 75 for that. It's not the end of the world if you do. I may or may not, I'm certainly going to look at outliers when I analyze the data, but I may or may not catch if that exactly happens. It should tell you as you're sliding it, what that number actually corresponds to there. It doesn't add it up for you. That's a feature. You have to write JavaScript, and I just didn't feel like it on Tuesday. Um, and then it would be nice if you provided some comments. The comments you provide, I will, unless you say something I don't want to share with your class, I will be just collecting them. They're all anonymous, and then just sharing them with the teams as part of the Canvas grade for the project. Um, and you'll just be doing that. We'll be kind of skipping around, but it should keep track of that. So if I go from here and I go to next, and then I go back, and that's now team three. I go back to previous here. It should have those scores. For some reason, the numbers kind of disappear when you go from one page back to the next, but they're still there. They're just not being displayed by default when you go from left to right. So we'll be starting with team two today, then 4, 6, 8, then 1, 3, 5, 7. And you'll be skipping around a little bit, but it won't be too bad there. And I had mentioned this, but just to confirm, and I could probably check this if you wind up doing this. I don't ask what your team is. I know all your net IDs and what your team number is. You don't need, and you're not expected to, and you shouldn't be filling it out for your own team. So you have your own individual self-assessment. That's in the slide. That can help guide your peers here in terms of, well, here's how we believe we did, and consequently, here's how you should think we did. Um, and there's enough of us, it wouldn't be the end of the world if you filled out an assessment for yourself. I would probably catch it, but even if you did, but that's not the intention. So you're not grading yourself. You're giving a self-assessment as part of your presentation, and then we're going to take 2 to 3 minutes and have your peers do that. So that is the goal for today. And I'd like each team to share their screen. We'll try it. If there's some weird failure case, I'll just go back to doing it myself. But the goal would be for each team to then share their own screen, starting with group 2 here. And in terms of live demo, Jared, if you have some videos, that'd be great. Whatever you have in the slides is what I plan on going through. So I don't expect you to have the board open and putting things on the board. That'd be cool. It's just not worth the effort. It's not worth the overhead. It's not worth the pain of things not working. So video is how we've been doing things for that, and that's how I'd like to continue it. So hopefully teams are a little organized, a little bit of pressure on group 2 because you're first here. So one of you should be sharing your screen, and you can do that now. And if there's not any other questions, please do get started, group 2.
All right, good morning, everyone. I'm gonna go ahead and share my screen. You guys should be able to see it now. Oh.
You might have some like animation or
something. Gotcha.
It's good and we can see it. You can continue.
Yep, awesome. So we are team 2. Christian was the one working on Ethernet and memory subsystems. Maggie was working on a little bit of everything. Ryan was working on the video and Ethernet subsystems, and I was mainly working on the memory subsystem. So our project is to migrate the SGP system from the Nexus video that we've been working on this whole semester, and then trying to port that to the Zynq UltraScale. So our main goal was kind of hopefully allowing students to maybe worry less about time enclosures and not have to worry about how much space there's left on the board. But this turned out to be a little bit harder than we thought it'd be. We ran into a lot of licensing issues, but some of it did end up working. So the first system we're going to talk about is the memory subsystem. This was probably one of the easier subsystems to get going. We initially were kind of debating whether or not to add this memory interface block, but we ended up just adding the CDMA blocks and then using kind of Vivado to run connection automation and block automation. And then we also used a Smart Connect block to directly connect to the MPSoC. And then we didn't have Ethernet working at the time, so we had to use Vitis to write some code to test that memory was working. And we were able to run a application project that tests memory, and it did pass. So you'll see in the screenshot to the right. And then we did package this and push it to Git.
All right, the Ethernet subsystem, there's a lot to talk about. On this board, there is a processing system and a programming logic method of accessing the Ethernet ports. One's the processing system being an RJ45 port, the programming logic being a SFP plus module. Some of the limitations that we first encountered were that the processing system required a Linux OS. Much later, as in around 3 in the morning, I discovered that you could also write bare metal C code to kind of act as that driver. So that would be a possibility that we could further explore. But that is one requirement. So if we were to go with the bare metal process, it would add to the whole tool flow of building a bit stream, exporting the hardware wrapper, sending it to Vitis, and then programming the board through there. And then another issue we ran into was that all the programming logic examples utilized an IP core that required an additional license. Dr. Zambrino sent us an open source repo that recreated one of those cores in Verilog itself, issue being that it was configured for 10 gigabit. We started porting that over. So we modified some of the components to go from 10 gigabit down to 1 gigabit. And then we kind of got stuck as we were researching and modifying a lot of the actual Ethernet stack and physical controller protocol devices, which none of us were too aware of. So that's kind of where it was a significant time sink, and we could get it working. We would just need a lot more time to understand these protocols a lot better.
So yeah, the video subsystem, like I said, or like was mentioned, this is what I primarily worked on. So on the top right-hand corner, that is the essentially the entire basis of the HDMI project, or the video subsystem, relied on this HDMI transmitter subsystem core that is provided by Xilinx, or yeah, and Vivado. However, it requires a paid for license, which we didn't realize until we were trying to synthesize, and it failed to like generate a bit stream and everything. The top project, or the picture in the top right hand corner, is the example project generated, or like the example, yeah, project generated by the IP core. Theoretically, this should work had we had the license, but alas, it couldn't. My next course of action was to attempt to use the IP cores that were used in the SGP system on the Nexus video board. However, those IP cores weren't compatible with our board themselves, so that was kind of a bust. And then I think the only option, if we didn't want to buy a license for the HDMI transmitter core, would be to build it from the ground up. However, going through and learning the HDMI protocol and standard was a lot more, or would have taken a lot more time than we actually had.
You can never really figure out when Xilinx decides that a core should be licensed or free, and who's making that decision, and why they make users of this board that you've purchased go through these extra hoops to license IP that is necessary to get things working on the board. It would have been good to catch that early on, because I have the license, but we haven't installed it, and so you didn't get a chance to try that.
So for the graphics subsystem, we just really didn't have time to test it. We would have needed a bare metal code to write the vertex data into the memory spaces and then compare the output to what the Nexus implementation would then output from render output. It's most likely functional, but we can't necessarily say it is. And considering all the design is device agnostic. So that's our beautiful diagram in all its glory. So we did get some data. You can see that the synthesis elapsed time for both are around the same, where the implementation elapsed time was significantly faster for the Zynq UltraScale. The generate bit stream was a little bit faster, and then LUT usage is 56,393, so a bit less than the Nexus video. The worst negative slack is the biggest difference, and it's +3 for the Zynq UltraScale, which in our opinion makes it worth implementing. You can say.
So it's got fewer resources that it's using because some parts of the design got stripped out. Would that be the case?
Right.
Like the,
Right. It's not a completely fair comparison. However, the graphics subsystem is what causes most of the issues in our design. So it's a relatively fair assumption to say if we were to add all the other subsystems, our worst negative slack and synthesis time should not significantly worsen. Daniel, can you move on to the next slide? But yeah, going into our self-assessment, we graded ourselves on a pretty black and white scale of it worked or it didn't. We kind of set ourselves up there with our rubric. There wasn't really much leeway. So that's kind of where we put ourselves. We put it at 150. The Ethernet and video subsystems, we have designs that we either know could be functional, whether with Ethernet, whether it be we purchase a PCIe SFP plus module, and then we could actually start debugging that way. Or with the video subsystem, if we had an extra 6 hours and Dr. Zambrino could install that license. So they're there, they just aren't tested, and therefore we can't classify them as functional in any way, shape, or form. The memory subsystem we were able to test. As for Git integration, everything that we've worked on has been or will be packaged just into Tickle scripts, just as we did for the lab infrastructure, and that'll be publicly available. And in our report specifically, we're highlighting a more in detail reasoning as to why we believe the conclusion we came to, which overall is, if we were able to get that license and it wouldn't be too much of a headache for the HDMI system, pursuing this further and getting the Ethernet subsystem working might be worthwhile, especially since future 480 students wouldn't be spending hours on bitstream generations, implementations, and they wouldn't have to fight timing closures quite as much. Granted, it's a big process getting that Ethernet subsystem working. We have some good ideas as to where to tackle next. It's just more of a question of, is that bare metal approach in Vitis valid, or are we trying to do a full programming logic stack? And that would be discussions to have with Dr. Zambrino for future work.
All right, thank you, team. And so everyone should have their Qualtrics open, and we're right on time. Have your Qualtrics open. Maybe you've already been doing that survey as they've been talking, and that's fine as well. But if you haven't, just take a minute here. Can the next team get your screen share also going? And you can actually leave it on this slide just for another minute before you get started here. So those who are looking and filling out the survey right now, you don't have to provide comments. It's not a requirement. If your comment is good try, that's fine too. It doesn't have to be super thorough, detailed, but if you had any thoughts, feel free to share them with the team. Otherwise, for this group, that since we got started a second or two late here, let's just take about 1 more minute. If you have any questions, this would be a good time to ask. Otherwise, we'll take 1 minute and we'll go on to the next team. So Micah, there should be a left and right, or like a next and back button near the bottom of the Team 1 survey. And if there's not, there's a possibility that same thing you're seeing is what I was seeing, which was you clicked on the survey maybe on Tuesday. It wasn't, I was still editing some aspects, and now it's like some cached version of it. And so if you're still seeing that, that would be the next thing to try. Try an incognito or private window of some sort, or a different browser seemed to work for me as well. Then it'll give you a fresh survey. Okay, it's there at the bottom. Great. So I'll say congrats, Team 2. This was a speculative project. If it was doable, I would have already done it. Or if it was easily doable, I would have already done it. And so you ran into some challenges. I overcame some still to be overcome, such as life. Team number 4, you can get started.
All right, morning, everybody. So we're group 4. So I'm Jared. I did focused on the depth testing, and then also helped AJ out with his OpenGL application, some troubleshooting. Ben did the texture mapping and did our report. Dawson focused on alpha blending and then also broke his collarbone. And then AJ's main goal was getting Super Hexagon ported over to the FPGA. So this is what we're going for. This is a GIF from the Super Hexagon GitHub. This is what it looks like playing on, for example, the Switch. We're going for something like that. So we'll just show our final demo, but this is what we ended up with. Those are just some fun bugs at the end. So some of the issues we ran into while we were working on it. And they're the same picture, so clearly we did really well. All right, so for some challenges, I'll talk about the depth testing one because that's what I focused on, but then alpha blending and stuff we'll let everybody else touch on. So one of our biggest issues was back in MP 1 or whatever, we set up the like the viewport and we just did X and Y. So we spent a lot of time figuring out why it wasn't reading Z. And so turns out it's never going to read a good Z value if you don't actually write the Z value. So that was a pain to find, super hard to figure out. You have to go way back, and simulation like isn't going to show that all the time. Addresses just not lining up, so that one was pretty easy fix. And then we had a lot of areas where we forgot that we should be using a fixed point math.
So I guess the next thing on this slide is like getting it to even compile. And so I had just a crazy amount of issues with this. Mostly, most of them came from just my old code and it being bad. And I'll talk about this more on the next slide. But we basically had to, or I had to rewrite just a lot of it. So then who else has?
So for alpha blending, we had issues. You go ahead, Dawes, if you want.
Yeah, I'm the alpha blending guy. At least this is my part. So for alpha blending, we had a couple problems. We almost had it done in MP4, but sadly we had a issue where we did a test and it seemed like the alpha channel was being driven by the red channel, but looking through the code, there was nowhere that was super obvious about alpha being set as red. So we simulated it and simulated it and simulated it. And we even used Blender to try and see, given, or we have the logic correct for blending, but how can we get what we're seeing on the screen by messing up the inputs and the outputs for inputs to the blending and output to the screen. So that took a while, and just turns out that we were reading from the input fragment wrong and writing to the color buffer in the wrong order. And somehow it was still working beforehand with correct colors and all that. But that was the main issue that we had that we couldn't really find until Zambrino sent us his, how he read the input fragment and wrote to the color buffer. But once we found out how to get that, it was really sad that we wasted so much time on it. And then Ben, if you want to do textures.
So textures, we didn't really get to textures till Tuesday, so we weren't able to test them very much. But we do have, we think, most of the infrastructure for that implemented. We have our driver code to write textures to memory. We do have all of the hardware, we believe, for textures, and it does simulate roughly how we would expect. However, for some reason, currently, if we turn textures on, it does lock up our board. So we haven't been able to really test it. And like I said, we just got to this Tuesday, so we didn't really have time to dive into debugging it either. But we do have most of the infrastructure in place for it.
So with OpenGL stuff, we decided to port like a pretty old program of mine that I've kind of worked on for a long time. And I'm sure many of you have gone back and looked at your own code and go like, wow, that's garbage. And this was a case of that, because a lot of the stuff in my quote unquote engine was completely hard coded. And after basically going through this course and kind of learning like more of the intricacies of OpenGL and how things work, I decided to rewrite a lot of the way the draw calls work. So before, everything was kind of baked into the logic, and now it draws to a surface and then can transform using matrices at the very end, which, you know, when I originally wrote the application, doing it this way would have made more sense, but I had basically this one course in linear algebra and I never really connected the dots with transforms. So I spent like literally 2 days rewriting that. And then once that was done, I was able to connect all of the OpenGL and infrastructure stuff. And we still ran into a lot of problems. We ripped out our shader core, and for some reason, shaders were still breaking our driver. And then we realized we didn't actually rip out our shader core because somebody was using an older version or something like that. And so it turns out that our shaders are just broken, and it took me like 4 or 5 hours to figure that out. But hey, it works-ish now, so that's pretty cool.
So looking at old code and seeing it's garbage is one thing. You'll also eventually encounter looking at old code and saying, wow, that's genius. I don't understand it. I'm no longer smart enough to understand the code I wrote 20 years ago. So that'll happen to you eventually as well.
Yeah. So works both ways, definitely.
So here's a look at our rubric. We had the really great section marked as playable. It's playable. You just have to be a little patient because it's coming in at about 1 frame per second. But our biggest goal was, hey, we want to get walls drawn, and we want like the person to be actually able to control the cursor. So we got that. Resizable vertices. This was one of like the technical challenges that we wanted to overcome, to make sure that we were not writing more vertices than we needed to, which would really hinder the board's performance. And so I think part of it, why it ended up being even 1 frame per second and not 1 frame every like 30 seconds, was the fact that we were able to only write vertices that we needed, because it writes all the vertices, or I believe the way the game works, and AJ can probably explain a little bit more how he did it, is it would write all the vertices for the walls before they would show up on the screen.
Yeah,
And
the
then-
original intention was that there's a fixed size array. And this kind of like the red triangle works this way, where you have a fixed size array and you just kind of render it. But the way it works now is, yeah, there's a vector, and it can pre-compute all of the vertices, and it only uploads those vertices that it needs to the board, instead of appending either a bajillion empty vertices, or you say, hey, we have a fixed size of maybe 8,000 vertices, and then when you hit that limit, it just chops off the rest of them. But now it actually does really consider how much you're pushing to the board. So.
And then as far as driver implementation, we had most of the features we wanted. And the game, we didn't show it in our presentation, but the game does render on the PC standalone. And the one thing we didn't get was supporting multiple draw calls on there. So everything else was fine. And then texturing, we put in some attempt, but it was just straight up not working. So we like a little bit more than 25. So.
Okay, great. Any questions for this team as you're filling out your assessments? Thanks, team. It was pretty cool to see, just, and it's true for all the teams, but just kind of following, random camera pictures or screenshots you're sharing in your channels. And for this one, maybe you knew better than I did in terms of how close it was, but it looked like triangle garbage, and then all of a sudden one last change in it looked exactly right. And I don't know what that maybe final bug fix was that went from Asteroids to this game. Do you recall?
So the Asteroids one, I can't recall specifically, but AJ did run into an issue where we found out that the order of the way you call and bind your OpenGL arrays is very important. And if you try and bind 2 before you're done with them, it ends up using just whatever the last one you bound was. So for example, ours was color. So the positional data was actually being written by the color data. So it ended up with some weird stuff happening in the top.
So that thing where we just had the driver, and I never actually saw it, just print out, here's every single call that's happening in the order that they're happening, helped kind of track that down.
Well, actually,
no.
So for that one, it did help a little bit, and then I made it work exactly the same, and then all it turns out was like, okay, everything's exactly the same. What's truly different here? And it turns out that the shaders that work for the Switch very much don't work for this
just the
case.
shader then.
And so, yeah, I literally just copied and pasted the shaders in, and then it started working, and we're like, oh crap. this bit file actually has the shader cores in it still, and it's not doing a direct pass through like we thought. So they worked on the computer and they work on the Nintendo Switch, but they didn't work for SGP infrastructure. And that was a lot of the problem, right? Is you would see something work on the computer and then it just does not work at all on SGP. So.
All right, congratulations, team. I think you should feel proud about this. So you've ported that game to many platforms now, and now it's being ported to this bespoke FPGA-based platform and getting you a solid 1 frame per second. So, we do have to move on the interest of time. So hopefully everyone was able to fill out their survey for team number 4. And next up, someone from team 6, can you get started by sharing your screen?
All right, you should be able to see it.
Yep.
All right. So we're group 6. Our project was anti-aliasing. So our initial goal was to implement 2x super sampling AA. And that's when you basically double the resolution and then average 4 pixels down to something. But then we kind of realized, like after looking more in depth, that MSAA is actually probably easier in our case. So what MSAA does is it increases the number of tests per fragment. So currently, what like most people's SGP does is it tests one like point in each fragment to see if it's either inside or outside the triangle. But what ours does with AA is it tests 4 separate points, and you can maybe see that there in that image on the right. It tests 4 separate points, and then depending on how many of those points within that fragment pass, it shades that color or shades that fragment differently. And then there's some pictures of anti-aliasing. Thanks.
Yeah, so some of our major technical milestones where we got triangle fans and strips working. That was a big thing because we had, like, as you'll see on like the next slide, we had some problems with like flickering. We got depth blending and alpha blending working. We were very close for MP4, but we just like needed an extra day or 2, I think, to get those generally working, and then an extra week or so to get everything ironed out. Anti-aliasing, we got it working. Well, we got the hardware implemented and it didn't completely break our hardware. That was a big thing for our group because every other time we tried implementing, it like completely broke our hardware the first time we tried running it, and we got like nothing on the screen. And then we finally got like a triangle to anti-alias, and that was the last thing. This is me too. Yeah, so it was very exciting getting this working. Play the video, yeah. That's what it looked like before we got our like triangle strips and fans working. We had something up with our primitive assembly and it kept like switching the last and first vertices. And then we added like our polling thing. So it waits for everything to be done before it continues on, like for each IP to be done. And that fixed it for us. You want to go to the next one?
So once we got the primitive assembly working, we still found a few bugs with the vertex shader. It took a long time. The bugs were just so small. One of them we missed the ×4. So that picture with the cube, with the really wonky cube on the far left, this was our original shader for the cube flyby. We had to make it really small, or else the triangles would just go out of the screen and be really nuts. And then as soon as we added that one little change, our cube just started looking normal again. It was a little bloated, but it was a lot better. And then we found out that we forgot to not write to a cache, and that writing issue had solved the sizing, and that's how we were able to get the other, like the FlexDL and the Falcon working. Which, by the way, those took. There's a reason why we don't have videos Sonic took about a minute to render, and the Falcon took about 15 minutes to render.
How many triangles are in the Falcon, you recall, just roughly?
About 148,000.
Well, when it's measured in minutes, I guess you can calculate your triangle rate pretty effectively just with the stopwatch.
That's for sure.
Yeah, so the other things we like practice or like got working from the MP2 to 4 was depth testing and alpha blending. For depth testing, we forgot to set the memory signal back. Like forgot to set the yeah. So we when we were writing it, we never set like the writing signal back to 0. So we were like reading and writing, or like they thought we were like reading and writing at the same time. We were like just storing and loading everything in. We also copy and pasting kind of bites you in the butt here. I forgot to change the SGP-GL disable inside of the depth function in GLX trace to the actual SGP depth func call. So we were enabling it and then we were setting the depth function and then that was immediately disabling it. So we were getting nothing to show. It was very, very frustrating. And then for alpha blending, we got that working and Josh did a lot of stuff to fix that after we got it like pretty well working. But the biggest problem was we were doing everything in fixed and then we weren't multiplying by 255 and truncating correctly. And once we started doing that, it started working a lot better and didn't just give us black triangles anymore.
And I think I did also have the same problem that I think group 4 did, where we were reading in the value from memory as like ARGB, but we were setting it like not right since the value in memory was like ARBG or something like that. And I had to figure that all out, but I think we had that same problem.
All right, so here's for our actual target focus for our project, MSAA, as Josh already touched on the first slide. Essentially, the idea is we just test each fragment multiple times at different locations so that we can theoretically get better colors to show up at the edges of triangles where otherwise it wouldn't show up at all. And we do have a couple demos for that, but we're going to go into the hardware about that first on the next slide.
Yeah, the biggest change that we made, we didn't want to take up any more time than we were, because 15 minutes to render a 3D model is just way too much. Unless you're Pixar and you can just offload it to a million machines just somewhere on. So we chose to divide up the work into 4 triangle test cores, and these are all configured so that they each do one of the samples. Yeah, after the triangle test is done, we count all of the tests that pass, and those are all mixed in the render output.
And here in the render output, based on that value that's calculated in rasterization, we're storing that value in a attribute in our fragment as well. We just thought that was the easiest way of doing it. So, and since we weren't using like the later half of the attributes, so or the vertex fragments. So here in render output, we take in the value, and then based on the strength or like the number of tests passed, it's a different percentage. So I just have a bunch of states here, and it like averages out the percents based on what's already in the color buffer and then also the fragment that's coming in. So it's either a 1/4% where it's 25% of the source and 75% of the destination and so on. So I think here's a video of AA being enabled. It's kind of hard to see, but they are a little bit, yeah, there we go.
That was one of the biggest challenges for this project, was just proving to ourselves that it worked.
Yeah. So what we did to do that, actually, I don't know if this is my slide. I think it's Raphael's.
Yeah, so this is just Josh did a little hardware changes where the blending percentage just gets turned into like a solid color. So every cyan pixel that you see is ideally unchanged from the non-anti-alias version. And every pixel that's either green, blue, or yellow, depending on the chart there, is blending a certain amount.
That's a very cool
So-
demo. So that, I mean, so it's really hard to subtle to see the kind of shades certainly on the screen, but just by hard coding the result, you can clearly see the changes to the pixels that are getting made here.
Yeah, and I think it's really cool down here on the bottom. You can see that it's clearly going from like 100% down to 75, down to 50, down to 25, down to 0. I think like this bottom picture really shows how anti-alias is working. This top picture, it's, I don't know, that's kind of just random or seemingly random, but clearly it's working. So here's some of our testing that we did. So on this top one, we're showing that the number of fragments passed is changing from 0, 2 to 4 to 3. So it's clearly that kind of showed that our triangle tests were working. And then down here, this shows the averaging of the colors. So like an A color is averaged with, or I guess, I don't know, this R is averaged with this R and it's at 0.5%. So we would expect a half value, which it is. So that kind of helped us see that our hardware was working.
All right, move on to your rubric. Yeah, thanks guys.
Yeah. And then here's our rubric. So we did put a lot of work into fixing MP2 to 4. And we fixed a lot of it, but I think the problems we were running into later on was trying to get it to work all together. And we did fix like things like prim assembly, render output with the alpha blending and depth testing. So I think that's why we chose that one. Super sampling, I guess this probably should say multi-sampling. I think we definitely showed that we did that. We got that working as much as we'd expect. It was kind of hard to show, but I think the demo that we did show kind of showed that it was working. And then someone wants to talk about driver and OpenGL.
Yeah, so the driver, we got all the hooks in there. We added a hook to test, like to change the offset, which I actually think we took out, but we have all the calls. It was really simple, a lot more simple than we thought. We just added an enable for the anti-aliasing. And then the OpenGL, I made a few OpenGL tests that were not complicated, but tested a few edge cases of the like anti-aliasing with like depth and alpha blending or testing, but we weren't able to get multiple triangles to render with anti-aliasing as well. So we weren't able to like test it with those. And then TCL script, TCL, Josh and Micah both did a really good job testing the render output and like rasterization with those before they committed everything.
Yeah, so I think that's that. Any questions?
Says everyone fills out the rubric. We're okay for time. So you took a little bit longer, but you had a lot to talk about. You wouldn't say that you got 2 or more like subsystems more functional. You only give yourself satisfactory for that first attribute.
Yeah, I think our main point on that one was like it doesn't work like together. Like we don't anti-alias and depth test or anti-alias and alpha blend, I think was.
Yeah, that render output logic
We
is
did.
starting to get very complicated, right? For your
Yeah.
team, for a number of teams.
Yeah,
as
we have
well.
a lot of states in
Yeah.
there now, for sure.
Okay, other questions for group 6?
Yeah.
Very cool demo. I mean, I'm happy to hear that, as you added those extra triangle tests, that didn't completely mess up your placing and routing and your timing. It just never was an issue for your team.
Not really. I think our worst negative slack is still the vertex shader, where we like multiply. Surprisingly enough, that's like our worst negative slack. So that didn't end up being a problem with anti-aliasing. I think we did run into a few problems with triangle tests though, because it does have to run in one clock cycle. So We had to change some stuff there.
Okay.
All right.
Excellent. Well, you can end your screen share. Thanks, team. And take a moment if you haven't filled out the surveys yet for Team 6. That was pretty cool, guys. I mean, it's great to see these complex designs working on your hardware. I'm sure for every team, given an extra day, an extra week, whatever, and if all teams had put, fixing MP2 through MP4 on the rubric, maybe every team would have also then focused on that as well. But that was cool to see that was a worthwhile investment. That it's just a lot more fun and easy to test when you don't have everything just be this glitchy kind of partially working thing. So that was very cool to see. All right, team number 8. If you're all here, please feel free to get started.
Yeah. So we sort of went after some performance improvements, specifically in the Vertex shader, and those are coupled with compiler improvements. And then we wanted to add performance counters to sort of verify that we were actually doing something.
All right, so the first compiler improvement that we went for was we went through and saw that there was like this matrix vertex multiplication that happened multiple times, and so that's sort of the 12 instructions there on the left, and we decided that we could do that in much simpler, and so that's in the top right is the instruction that we added to our vertex shader core. So it takes our 12 instructions for that and reduces it down to 4.
Yeah, and then we also implemented something so they sort of like came together. So insert 2 is one. So we saw this pattern of 4 inserts, and we're like, oh, we could optimize that. And then even there, we added in these swizzles that they were working with. So we're able to take that and combine it down into 2 insert 2 instructions, which it needed an extra stage to read in more values. So we added that to the Vertex shader. And this is able to reduce the number of instructions needed and the number of cycles in particular pretty drastically. So if we look at it, so we can see this is a regular insert. Here's an insert 2. It takes 1 more cycle to run actually, but when you get rid of the 4 to the 2 that you need, it saves you about 40%. So that was really cool. And then when we did other compiler changes to get rid of the swizzles, there's even a bigger performance improvement. And then here, this is when we got rid of this to the new insert, the flip cert, as I called it. So basically what it did the exact same thing, but in 1 cycle that was of standard length. So that compared to the 2 insert 2s, that's like an 85% improvement, and compared to with the swizzles, there's an 85% improvement, but compared to just like the 2 insert 2s by themselves when the compiler optimized it, it's about another 40%.
And then in order to measure, the performance of our system, we went to add hardware counters to the main cores, the Vertex shader, viewport, rasterizer, and render output. And Aaron had the great idea of, since we weren't using attribute 3, just storing how many clock cycles it took for each core as we passed the vertices down the pipeline. And that's in the bottom left, Vertex shader on X, viewport on Y, and on. And then the thing on the right is just an example of one of those counters from the Vertex shader core.
Sorry, do you hear me? I didn't realize I was muted. Okay.
We can hear you.
Something I should add, but that we didn't really get to, was that the other thing we would do with the hardware counter is that because it's being written to the vertex already, we were thinking that in render output, we could write that attribute 3 straight to color buffer 3 because we weren't using that either. And then it could maybe act as some sort of heat map. We weren't able to get that working, but that was also an idea we had in mind. Here's the compiler update, and it was very hacky because when I asked Steve about the compiler, basically the original plan was to modify the Lua code, but he basically showed me that it's pretty dangerous to do that because it cascades. I guess there's like a lot of problems that happen down
I just feel bad
the
about
road.
this part because I saw his comment there and then he and I separately talked about that. I think you and he were talking at complete cross purposes here when he says, wouldn't mess with. Um, I don't think that's what he meant. So, and he wasn't very clear about it. So you could definitely get this working, what you're doing with regexes and just trying to do, string replaces in the generated assembly. But it wasn't necessary because I think you could have, you were perfectly allowed to mess with the Lua script. I mean, what's the downside here, right? So you generate assembly, shader code, and it's wrong. Well, so what, right? It's fine. It's something you would test and debug and try to figure out why things are wrong. Because that would have probably been a lot easier to take the assembler for the matrix vector multiplication and replace it with your new instructions. Same for the insert patterns and things like that. It would have been a lot less of a headache to deal with than to just worry about all the string management that has to go with applying regexes and then reassembly.
Yeah, I agree. When we were debugging, or when I was debugging, I saw that, Bryce wrote some regex code for me, and it was working in our test scripts, but I would run it on certain other shaders, and it would find patterns I didn't think existed, and then just replace those with instructions that shouldn't be there. But the upside to this is that within the driver, there is kind of just a find and replace generic function now. So if anyone ever needs to insert anything into I guess you could always insert something into the shader manually, but if you would want to implement your own instruction, the amount of effort is really small because you would pretty much search for it with regex. You would call the function search for it with regex, and then you would just add the opcode to the Lua file, and then that it would pretty much support your instruction.
Yeah, the flow seems a little not quite right yet because I think the Lua, it returns the assembly source, but it doesn't. If you modify that, there's no way to pass it back to the Lua to then generate the binary, right? Or I mean, that flow is kind of we give everything to Lua land and then we get everything back. We don't handshake with it beyond that.
Basically, there's a point in between where it's passing it from the Lua outputs to print out the string. The Lua outputs the pointer to the assembly, so I can just directly hijack it as I wrote here. So that's what I ended up having to do.
Cool.
Oh, and then the other driver updates, I guess this is also part of the performance profiler, but we wanted to analyze the cycles per instruction specifically of all the components or specifically our vertex shader, and I was able to get something done here in the driver, but because our hardware had issues with building, I wasn't really able to test it. You can see these really massive numbers, and I think those are completely wrong. That's just I just ran that with SGP none, so that's not valid. Another update I did was at the end of all of the SGP graphics map, the graphics state, there's a dedicated section for performance counters now, and also there's the heat map that we attempted that I talked about.
So yeah, at the end of our project, we sort of thought we were in between the 2 and 3 hardware optimizations because one was sort of an evolution of the other. And then we made compiler changes to implement some of these things. So they sort of went hand in hand. And then we did add hardware counters, performance counters for the render output and vertex shader, and the driver functions are there to read those and calculate some results. And we sort of ran out of time to get a benchmark working really well, but our report looks nice. So there's that.
Thanks, team. And to be honest, for what you were doing, it's probably preferable to do it on the board and to be showing real improvements. That would have been ideal, but simulation is still pretty helpful too, right? To show that if we were to do this sequence of instructions versus this other sequence in the abstract and simulation, that we get this. It's still quite I think that's quite valuable. Nothing you propose is something it all sounds very doable in terms of compiler optimizations leading to a slightly tighter instruction set that leads to shading improvements. I think that's totally, a valid accomplishment here. Any questions for Team 8? We're doing good. We're back on schedule. Let's take just a minute and you can fill out your surveys before we move on to team number 1 here. Yeah, regular expressions is not how I would do that. I mean, there are a lot of compilers that people try to build using that. It's tricky. So there tends to be downsides to that approach, but it's like a quick insertion hack to get certain subly strings swapped. That's, it's as good approach as any. You have to give yourself enough time to deal with string allocation and seg faults in C, and that can be quite painful. Certainly when you're tired and it's 3 in the morning, that could be quite painful. All right, you can end your screen share, team number 8, and congratulations, we made it. Team number 1, when you get a chance, one of you share your screen, and when you are ready, you may get started. I see an Apple background. There we go. We can see it.
Okay, so we're team 1, and in honor of our extremely successful, joyful project, we picked a bunch of dead companies to represent our icons for the last 2 weeks of the class. So our project was to implement deferred shading into our system. So essentially the point of deferred shading is to reduce the lighting costs for complex lighting scenes, especially ones that involve lots of fragments and lots of lights. So the idea here is that we actually can calculate and pre-compute a whole bunch of values relating to lighting calculations ahead of our actual lighting computation. And that way, in a second pass, we can simply iterate over the actual pixels that are going to be displayed to the screen and calculate lighting for each pixel rather than each fragment. And this kind of reduces the time complexity down from essentially polynomial time, because it would be fragments times lights to linear time, which makes it significantly more efficient. So coming into this project, I think we kind of were very unprepared for what exactly we would need to do. We kind of tried to define our project as best as possible and figure out what exactly we would need to change. But ultimately, we ended up having to spend a very significant amount of time simply learning exactly what deferred shading is, how it's typically implemented in OpenGL, and how we may actually implement that on our own hardware. Because as we actually figured out, the way that deferred shading is typically implemented really wouldn't have worked on our hardware as it is now without some substantial changes to lots of different systems, and we weren't really interested in that. In general, we decided we needed a fully functional shader core for both the fragment shader and the vertex shader. The shaders to support deferred rendering are significantly more complex than the majority of the shaders that we've worked with in the past. And similarly, the way that we decided to do it was to kind of render into texture memory and use that texture memory essentially as a G buffer. So we'll talk a little bit more about G buffers later, but we essentially decided we would need fully functioning textures for this, which ultimately we didn't end up getting working. But that, I think, yeah, that was one of the only unfortunate kind of failures we had. We also needed some driver changes in order to support multiple rendering strategies. We wanted the ability to be able to select between forward rendering, which is what we've been doing all semester, where you can calculate lightings in your fragment shader, as opposed to also supporting deferred rendering. And we wanted some, of course, some OpenGL examples that would demonstrate our work. So one of the first kind of big accomplishments we did is we drastically improved our shader core. We left MP3 thinking our shader core was very nearly done. And in fairness, it was, but we kind of had a little bit of a poor debugging strategy where I was essentially debugging it while other people were building more infrastructure to part of the graphics processor. And I didn't really fork off into a new branch. So essentially, I actually had it working, but then it was broken because of changes other people made to other parts of the system. And ended up that kind of back and forth set us back a substantial amount until by the time we're on this final project, we realized that there was still, a lot of work to be done on that. Driver's code that we thought was functioning was
I
not
feel like you're
actually-
throroing your team under the bus. I had it working
No,
in
no,
my
no.
branch, but the rest of the
No,
team,
it
they
was-
broke it on merge.
Problems were just obfuscated by, again, it was really more of an issue in how I was choosing to debug things. Like I debugged in a poor way. I should have isolated it. Point is, it was a huge time sink. In the end, we got it essentially fully working. We supported square root, power, division functions because we needed those for some deferred rendering, tasks. We also supported uniforms fully. That was not working as of MP4. We had some strange issues when we tried to combine uniforms. Like I tested them pretty extensively, like individually or even with multiple uniforms would work fine. But then I would run something like the whatever the moving triangle is and get that bottom image. So wasn't totally functioning, but it was very nearly there.
Yeah, so now we kind of get to about the what changes we made in the driver. So like Braden had mentioned, we had we gave our best foot forward for attempting to implement textures. So that included, obviously copying textures. And I guess one thing to mention too is that although we didn't necessarily need a fully implemented working textures, because ultimately we didn't actually need to be able to apply a texture from the driver's side to anything in the screen, because all of the data is staying GPU side and created GPU side. Ultimately, we thought it would be easier to fully implement textures since we didn't think it would be too much more work than we'd already have to do in order to get it working and being able to test it and whatnot. So you can see on the right there too, one thing we actually did that was really kind of a little bit strange was we decided to make every texture a standard size and a standard width. That made our constants and some of our metadata for our textures just really easy offsets. And then we ended up upscaling and downscaling any texture you wanted to put in if we were to support an actual regular texture. And ultimately, the math all works out in the end where you're not actually stretching a texture at all. It just is kind of funky and it just makes the implementation in hardware a little bit simpler. We also had some strange things happening with our caches. So since we were actually doing having more than one program, right? So we'd have two sets of shaders running, right? You'd run one set of shaders and then you would then reprogram with another set of two shaders and run that. Well, since we were writing values to actually other places in memory from the fragment shader or from the render output and then reading from fragment shader, we actually had to have all of our shader cores in sync. And then since everything has its own cache, we're having to do a lot of cache flushes, which really slowed us down. But ultimately, we need to make sure everything was in sync. Otherwise, you'd be pulling stale data from a cache because there is no cache coherency module between them all. And so I think that's the majority of that on there. But yeah, no, definitely just we had some interesting trade-offs between simplicity of implementation in the driver and or I'm sorry, in the hardware and flexibility in the driver / OpenGL side.
Yeah, so here's our render output changes. So there are three ways we go through render output. We'd either be doing our forward rendering, which is what our regular process would be, or we'd be doing a geometry pass or lighting pass. Geometry pass is where we store into our G buffer. So we wouldn't write to our frame buffer and we do a depth check there. The lighting pass doesn't need a depth check because we'd only be working on valid pixels. So we're just able to write directly to the frame buffer there, saving us a bit of time and a memory access. But for writing to the G buffers, we have to do 3 writes for the 3 attributes. So we write the position, normals, and albedo plus specular, since that's one attribute, in 3 separate writes. So we have to write, then wait for the response, and then write, wait for the response, and wait for response, just to make sure that everything's written properly. And everything up to there is mostly the same, with those blue circles being what was already there. And then the red representing the geometry pass and the green representing what would happen in our lighting pass. And our forward shading happens all the same time. So we'd go to our depth check, our destination depth data pull, and then we'd go to transform, do all that right to the frame buffer if it was a valid pixel, and then right to our depth buffer after that, and it would all work the same. And that was tested as well as the deferred rendering was.
Gotcha. So here is some of our OpenGL applications. We ended up making 2 of them. So the one on the left there is kind of, originally it was supposed to be Flex Seal. I ended up changing the model because I found out Flex Seal didn't actually include the normal information to it. But luckily Suzanne the monkey does, because when I went and initially modified kind of the function that loaded the object data. So then I added the normal, loading the normal information from the object file. And then luckily, there was an example from Learn OpenGL that we were able to kind of somewhat base our understanding on to create these various applications. And it was very helpful when working with the both the shaders for the lighting pass and the geometry pass, having some sort of baseline to that.
Yeah, and so we kind of have these 2 demos, right? So the one on the left that Nathan just spoke about, right, was kind of the ideal that we had created, right? You know, this is based off of, you know, OpenGL, what they recommend, you know, kind of the standard for how you would go about doing it with all the bells and whistles, right? That we wanted to be able to see, you know, how can we actually, you know, go above and beyond. But ultimately, though, we couldn't really just have this one because ultimately implementing that on our hardware was just unfeasible in the time, and, you know, with the knowledge that we had, we would have had to make even more significant changes, and ultimately too, it would have been a significant amount of work. So kind of, you had that one example of seeing, you know, what can we do with it? What does this look like? And for our own learning purposes. And then from the other side, though, we had this other application. So this other one was based off of the Cube Flyby, and it was kind of a reverse where, you know, instead of, you know, kind of going from something more complicated, we kind of started and said, okay, you know, what would we feasibly be able to support from the hardware on our hardware? What do we have to have in order to make this work? And then kind of, you know, work up from the ground there. And so this one actually was really, really beneficial in helping us figure out, you know, how to make sure that all the data coming through is correct, how we're making sure that, you know, we have our 2 passes going. So you can see at the top there is actually, we were testing out normals and outputting it there. And then at the bottom, you can actually see that's what's called a screen space quad, which is actually a little bit, you know, it's transformed right now, but normally that would be just straight across your screen, which you're actually applying the textures to. So this actually helped us figure out a really interesting bug that I'm still not 100% sure why it happens, but we were having issues sometimes that even if our shaders were compiling correctly, OpenGL didn't want to switch the shader or the shader program. So we would actually have our first shader program running for both shader passes, which is why you get the thing in the bottom left where it looks like basically it's treating this plane as a cube. And so those are some definitely interesting things, and we were able to find some additional bugs by having, you know, a really, really basic, just break it apart into pieces example. But then we were also able to kind of see, okay, you know, here's with all the bells and whistles on the other side, that maybe someday we could implement with a complex graphics processor, not quite a simple one.
Gotcha. So here's kind of some of the examples. Gotcha. See that? I'll go very quickly here. A lot of these were, this is for our ideal sample of the new, you know, Flex Monkey in this case now. One quick comment. You see that we have like a little comment that's just a D there. We ended up working with Zambrino when our shaders weren't compiling. And it turned out because we were editing on a Windows machine, saving, you know, uploading it to Git and then pulling it on Xilinx, it just freaked out when it tried to compile it.
And I'm still not 100% sure exactly what's wrong. I mean, that's not your fault that that's happening. What the exact encoding is, like which byte is wrong causing that other thing to fail, I don't actually know. So that's the fix. That's a hack. That's a workaround. I'm glad you have that in there.
Yeah. And then on the left here, We can see our G buffer, which is just a bunch of textures that the top is kind of like creating it. And then at the bottom there on the G buffer kind of square there is when in the lighting pass, we would then activate each textures and bind it. We can go on.
Okay, I'm just gonna gloss over this because I know we're kind of over time. But some biggest challenges we had is that we spent a massive amount of time doing tasks that we did not think would take us very long, namely debugging old components that we thought were very nearly working, which evidently were very nearly not working. I also think we picked a project that we didn't fully understand. No one in our group really understood what deferred shading was. We thought it would be easier than it was, and once we kind of got into it, realized that most of what was given to us wouldn't work. It kind of just got complicated from there, and we had to change lots and lots of things in different parts. That kind of added complexity.
Yeah, so here are some of our demos. At the top there, you see a example with a multi-source lights and one with single source. This is just to show off deferred rendering and what it can do, since all lighting would be done in post after the geometry pass in our lighting pass. And you see different representations of position, normals, and colors at the bottom there. That top right image was something that happened after a hardware change on Braden's end, that we weren't too sure about, but we saw the normals being represented there by the red coloring, and it was very surprising, to say the least, to see that. Just scary, really.
Can you go back to that before you bring up your rubric? I know we're short on time, and I told you to go faster, and now I'm slowing you back down. Okay, would it be correct to say you don't know entirely what that picture? So there's some triangle issues. That's not important, but
yeah,
what's your best understanding of what that picture is of? Because I think that's important to see to get a better feel for what you have working in hardware for deferred rendering.
Well, to be clear, what that's showing is that's showing the normal calculation. So normal, it's essentially the same image you see on the bottom in the middle. We were kind of just surprised it popped out. Essentially, this is what would have been written back to the G buffer had we had that switch enabled. For this particular run, we weren't actually intending to test it on the board. I think Nathan was running it independently using SGB none, and just happened to do a run mistakenly with the Ethernet on. And the fact that we got these values shows us that we're actually pushing the right values out. And if they're going to the output like we see here, that would also imply that they're going into the G buffers, had we had that toggle.
Right, that would be my takeaway, that output shows that you're extremely close, right? As soon as you can push that, in theory, you have to worry about getting multiple shaders working, things like that.
Our thought at least is, obviously we had a multiple shaders bug, which seemed to be something like OpenGL related, which implied we're probably doing something incorrectly. But beyond that, had we had the ability to actually have textures functioning, I genuinely think we would have been right there, because this was showing that our shaders that were doing all these calculations were doing the calculations correctly. They were pushing the data to where they needed to be, and it was simply just a matter of writing it back to that G buffer, which in reality was simply a texture unit, texture memory.
Thanks.
Yeah, so kind of getting back to our rubric, ultimately, I think, at the beginning, we definitely wrote this with in mind that, we really didn't know what we were getting into, and we kind of wrote our rubric in a way that, we could still, make progress without necessarily getting it all working in hardware, because we felt, it'd be awesome to get everything working in hardware, but we figured that we would likely fall short just because there'd be unforeseen circumstances, which, ended up happening. So we kind of gave ourselves, about accomplished, maybe a tiny bit more for the driver changes. We had everything implemented. We were in the process of testing things. We didn't give ourselves exemplary though, because even though we did have a switch to actually switch between a working switch between forward shading and our deferred shading, we didn't actually end up implementing an additional compiler instruction or an additional shading instruction, because ultimately we didn't think we actually needed it. Initially we thought that might be something beneficial, but we actually figured out that, hey, this isn't actually going to help us anymore so than just other optimizations would. For hardware updates, we understood the changes we needed to do. We had diagrams and we had plans for how we were going to do that. And we had, software rendering, is implemented, quote unquote, because software rendering, we kind of realized wasn't actually a really correct terminology for it or way of describing it. But for the most part, we had the majority of that implemented and planned out, just, not quite fully working and whatnot. OpenGL, you know, we had applications that made use of multiple light sources. I think that one that we showed in the previous slide was 10 lights at once. You know, we had we didn't quite have multiple objects, but that was also too because it was very slow doing tons of lighting calculations, especially for 10 lights and whatnot, and trying to figure out and get everything debugged. It was kind of complex, so we ended up just skipping over that. But you know, we were able to also toggle between that in our application between forward and reverse rendering pretty easily. And then finally, to our demo report, you know, we have a semi-functional demo. You know, we're close. We didn't quite make it all the way there. We really documented our driver changes though in our hardware updates. I think our lab document is just about 19 pages. So, you know, I think we really tried to make sure we documented everything we had, documented our applications, but ultimately our actual hardware implementation just wasn't 100%, although it was close.
All right, thank you, team. Any questions for group one? Yeah, there's normals there, but not textures. And I think I just removed the texture coordinates, so that would have been pretty easy to bring back if I'd known you needed them. Anyway, yes, so that's right. We spoke past each other on that point. So any questions for group one as you're filling out the rubric? Okay, well, lots of last minute work, but definitely a lot of progress made, obviously. And so in terms of how you wrote your rubric, and we should go back to the project proposal demo day that we had and the discussions had during that as well. But you know, you're able to salvage it based on how you wrote your rubric, and I think that was important to do.
Sorry for the long presentation.
Oh, it's fine. You had a lot you wanted to talk about, and we're okay as long as we stay on target here. We're just fine today. We got 3 more groups to go. Team number 3. Feel free to get started.
All right, can you see my screen?
Yes.
Awesome. All right, so we're group number 3. Me, myself, Justin, Nathan, and Sava. Our project was to try to get this guy's Minecraft weekend project, which was like, you know, making his own bootleg Minecraft in OpenGL. Was to try to get that running on the SGP. So pictured there was our ideal end state on the left, was getting Minecraft running on there. And also to some extent, yeah, Nathan fighting with Vivado and just generally making improvements on our design. So some of our technical milestones, initially, one of the first things we did was just kind of get the, you know, his Minecraft, bootleg Minecraft running on, you know, WSL and just, you know, running in general so that we could track to see what OpenGL functions it used, to see which ones we already had implemented and which ones we'd have to implement and maybe which ones we could like leave out if came to it. After that, we kind of worked on getting fragment shading and then getting our actual Minecraft to build and run on the Red Hat machine, which we kind of ran into some issues initially with like CMake, I think, and stuff along those lines. I think Justin has some of the other stuff for the technical milestones.
Oh, okay. So yeah, we actually did do the texture mapping infrastructure and the driver. We just didn't get a chance to actually implement it in the hardware. Along with that, we also made a more OpenGL compliant driver because the Minecraft basically only used GLDraw elements, which wasn't implemented for us already. So we had to also then include vertex array objects, support a lot more buffers, program shaders, etc. And along with that came improving vertex fetch and making it a bit more robust because we didn't want it to overflow the FIFOs. We also had to deal with the stride, a non-zero stride, and translating that into the GPU buffer. The next milestone we reached was actually having a perspective divider simulated. We didn't quite get it on the hardware yet. I believe Nathan was about to run a build for that, actually.
I was running a build until Vivado decided just everything is going to just crash and burn, and it's just clock rate doesn't match, and then it thinks this is a reset pin when it's just a 1-bit, all that stuff. Anyways.
Yeah, and then we also we're able to reprogram with multiple shaders and multiple different programs. We also did a zero cycle latency pass through just to speed up when we were debugging. And then the last one is, well, Minecraft does run in the SGP ETH, but we had to replace textures with a constant color. Otherwise, our shaders would lock up. And that's just kind of showing you that we did actually rate limit vertex fetch properly and the driver is fully complete. Yeah, so at the beginning of the project, we were kind of catching up on MP4, specifically just getting the fragment shader in the pipeline. We tried a lot of different things to lower the utilization and fan out. Ultimately, we eventually just decided to add a clocking wizard and underclock specifically just the SGP pipeline. And that was the only thing that actually ended up working for us. So
Well,
now do you have something to say, Nathan?
I think that it was really important that we fixed the BRAM utilization for register files. So a lot of the metrics that were poor in our implementation in the first place weren't actually utilization. It was kind of a red herring. So starting there wasn't the best idea, but I think it freed up space. So like if I had 2 more weeks, and maybe I'll mess around the next 2 weeks if the passwords don't change, and might be able to, throw in 4 fragment shaders because our utilization is quite low now, but it was just such an inefficient and high fan out design. Because I noticed, I think one of the biggest problems was just the register file. There's also some issues like the ALU and I forget, but after a refactor, the overall complexity of each of those went down. So that was like the very first thing I was working on, was just spending a lot of time fixing what was a burning garbage fire from MP4. And then, yeah.
Next part, just shader debugging, trying to figure out like what we actually needed to implement in those shaders and determining what we could actually leave out. Our driver seg faulted many times when we were debugging it. It was like just messing around with pointers and buffers. Another problem we were running into was different team members having different understandings of what the OpenGL spec was. A lot of the naming conventions we were getting confused about, like, oh, are you talking about the object versus the actual buffer? Another challenge we had was GL draw elements with the non-zero stride. We had to basically start from scratch with writing to vertex fetch to do that. Nathan's remote desktop randomly just totally got busted yesterday. Eventually I just had to log in and he used my account for that. And then
yeah, so then for this, you can see in the first screen is our draw elements test. So basically the bottom couple triangles, that's like 9 vertices. And on the top, they're the same. I have the same vertices, but I only decided to draw 3 of them. So on the top, we're using draw elements. In the bottom, we're just using regular draw arrays. And as explained before, draw elements basically uses an array object, then it uses an array of elements, which like index that vertex buffer object. And also like at 5 a.m. because of previously said revamps with like vertex fetch and all that, we were able to get like a couple of projects you can see in the bottom that like basically never worked. We got them to work like a couple hours ago, so that was pretty cool. And then yeah, on the right here you can see our Minecraft's sort of the first beginnings of a demo.
Yep.
With SGP non-running, and then I think Nathan has a demo.
Oh, I would definitely.
Ish.
Oh, we could attempt something live. It's really just SGP nom. I think the important disclaimer is this is proving, it's a pseudo proof of correctness of the driver. We've worked through it ourselves, stepped through a little bit of GDB, and then anything we could do with hardware to see what gets sent, but. The actual hardware running is much different. You'll see on the next slide what it actually looks like, but this is showing how our hardware can keep track with our driver
can keep track with the Minecraft game, which has quite a lot of just overall complexity in how many GL functions is calling, and a lot of state management and just total size of buffers that previously were a challenge. So I think it actually was kind of an accomplishment just to get it running in SGP none.
So let me ask the team, why do you think that connection between getting draw elements working, which is non-trivial, and the MP two applications is not that clear to me? Why do you think that's what allowed you to get Voronoi?
Well,
and
we rewrote the interfacing with the AXI MMS, like mapping to stream IP. So that's pretty much written from scratch, inspired by the original, but we redid any pointer arithmetic, fixing any issues that we had, and it also I think that's the big issue is it's easier to support that first offset pointer is one of the big ones. But it's just basically interesting to see like this morning that, oh, they work now. It wasn't the original intent, but
Right.
after re-implementing it from scratch with new and in the most important change for this attribute stuff, and I'm sorry I'm not really speaking well today, I think my brain's really fried, but is that we changed the buffer copying strategy, especially since that's one reason to segfault is the assumption that was made in the original implementation of the driver that you could copy the buffer data in GL attribute pointer, which isn't exactly true, since the user of the GL calls, JDA, the guy who made the Minecraft, was freeing his buffers right after calling GL buffer. So there's a little bit of extra management there, and then the actual implementation is doing it in multiple steps, is copying per attribute and kind of rearranging the attribute data to be linear in GPU memory so that DMAs are more appropriate to use. And even though, so that helps with draw arrays, and it has to be a little bit more complicated and less efficient for draw elements, but it's the best we could do so far.
Why don't you show us what Minecraft looks like on the
Well, you'll see. It's not really
Yeah.
So this is just showing we had to take out texture. So again, what's in hardware right now, because the majority of our work really ended up being driver logistics, driver boilerplate, state management, and just painful. It's kind of hard to branch off and do work on the hardware in parallel, especially when we're having issues with OpenGL spec and coordinating it. Plus everyone's kind of busy, so most of our success in like technical milestones really came in the driver. So we didn't have texture mapping actually finished at the moment. So this demonstration to show that it can run in ETH, we had to remove any texturing, which results in this obviously ugly, completely white drawing. So you can see on the desktop what it looks like. I'm not totally sure what the output of the hardware is, but we do have evidence from our driver that the data is making its way through our pipeline very slowly. You can actually see it waiting for the FIFO into Vertex Fetch. Whenever it's ready, it'll send stuff, and it's still waiting for our render output to say, hey, I've drawn this index and I'm done doing that. So it's doing those things, but there's definitely issues in the middle, both with probably shading, and then I think perspective divide could be a big issue. Given this giant white scene, it's very much possible that's kind of stretched out, but I think it's more complicated than that. But I think the big proof here was we could actually run it for several minutes, and it's stable, running multiple frames. It's not hung nor crashed. It's really proving driver correctness at this point, not hardware, as you can tell, because it's a white screen.
Okay. Why don't you bring up your rubric then? Thanks.
I think the way we wrote our rubric is kind of friendly towards us because we expected wholeheartedly not to have anything great draw to screen from the get-go. The fact that it's drawing so many vertices and so many buffers, and we didn't expect a lot on the output. So some of our criteria is written with the intention of limiting game features, limiting which, like how many things can be drawn. So we're definitely weakest in the hardware criteria. It's debatable whether you can say it's drawing to screen. I'm kind of measuring it based on, okay, my hardware is receiving all of these, it's doing the pipeline, but really the data is not correct. So
where you draw that line is actually kind of completely arbitrary. It's somewhere in definitely in the beginning category for the hardware. Our driver implements all the fundamental functions that we required for OpenGL, though not the exemplary category that we set for ourselves. We definitely couldn't have supported the original version of Minecraft like without modified Minecraft source code in our current version, because we've intentionally catered it and reduced functionality just a touch to work with what we can do with SGP. One just coincidental improvement in the hardware, as you'll notice, was robustness in both vertex fetch and shaders when I finally actually did fix the setting of shader shader program counters and flushing their cache such that you can run multiple programs on the same board session. So it actually, that did end up being like a subcategory of our exemplary goals that we touched. Software in terms of Minecraft modifications, we refactored Minecraft, some of the shaders. So if you actually were to look at the demonstration we did of SGP None, we actually have modified that to do certain mathematics differently, especially like the hard ones that we knew that we weren't going to easily support in our shader ALUs quite at the moment. Like power, we never implemented an MP3. So there's certain optimizations we did, but that didn't have visual detriment. At least I'm sure you're like, it looks kind of like Minecraft. That's what I thought. So for the most part, we got software Minecraft refactored to be functional, run, and I think the demonstration showed that when you run it, we can still do the break and build, although we didn't show a lot of that because it was a short GIF, but you can still play the game. It's very
I'm
limited.
gonna, so Nathan, thank you. I think I'm gonna cut you guys short here, or cut you guys to time here. Any questions for this team for group 3 as you're filling out your rubrics? This is a good time to ask.
So on a scale from 1 to 10, how much fun do you think it was to play?
Even in the original WSL version, it's so limited, and like it has like this terrible
The
mouse
hardest part is the mouse.
input. Yeah,
You can't control.
It's like
And
you have
the
to turn
latency
very
is
slowly.
very high.
So even when it was written originally, it was not written well for performance, nor was it fully complete Minecraft. But you can definitely build. It's cute. You can build a little grass, dirt, or stone hut, and you can dig down, dig sideways. But
Stellar game marketing is what I'm hearing.
yes,
Just needed redstone.
absolutely.
Well, I was gonna tell my Minecraft story. Thank you, Ryan, but you guys went a few minutes late, so no time for that today. Everyone, please fill out the group 3 rubric. And group 3, please stick around for the last 2 groups we have here today, but certainly get some sleep at some point. Reset. Your body's clocks and go off caffeine for a couple of days and just kind of reset things. It may take a couple of days, and it's good for your personal health. So I understand that. So I could tell, and we're all feeling a little bit of that. I get it, but certainly look after yourself as well. Team 5, it looks like you already have. Your slides up and running. We can see you, and so please feel free to get started.
Yeah, so we are Team 5. Can you hear me? Awesome.
Yes.
So we have kind of 2 things we're going to look at today. The first of which is face calling. Face calling is kind of a way to more efficiently draw 3D shapes by looking at the triangle rotation and using that to determine whether or not we want to pass the shape on from triangle setup into the rasterizer. So if you look at the lower left image, each of the triangles on the outside, if you're looking at it from the outside, should be counterclockwise. So the first one, the eye sees, is counterclockwise, but the back one, because it's the opposite face, is clockwise. We don't want to draw that, so we don't pass that through our triangle setup onwards. We ended up implementing this in our triangle setup because that already has the clockwise and counterclockwise rotations defined. To get this to work and have the options of the face calling, we created a bit mask. As seen on the right, you can see each of the bits. We have an enable and disable for the face calling, whether or not it's been changed to use a user defined or system default face calling values, which face you actually want to call, because in OpenGL you can use call face, GL call face to choose between the front and back, and then what direction defines the front. Different applications might have different defaults. We then use this to also go into the driver and tie in those function calls and pass them through to the hardware using the AXI buses. The other thing that we worked on was creating a software library for creating primitive shapes. We found that primitive shapes are kind of a pain to make because even for a simple cube, you're looking at least 36 points. And that's just if you want it to be like basic upright cube. We also added in rotation and other things to go along with that. Another big part of the software library is because we were doing face calling, we wanted all shapes, especially 3D ones, to match the exact same direction in their rotation when the user is looking at it. So every single triangle, if it's what you would call the front face, is counterclockwise by default.
All right, so for what we actually got done, our face calling hardware works, and we had some minor bugs, but we got those fixed. We implemented a variety of 2D and 3D shapes, such as cubes and pyramids, that we'll have some nice pictures of later on. And we had some tests and demonstrated pretty well, I think, that our stuff was working as expected.
So as mentioned previously, we had some bugs with the face calling, mostly when the user is defining front and back, the opposite triangle would be drawn. If you read closely on that our very first slide, you would see that we say user defined front counterclockwise, but we say front defined as anything as clockwise. That we had to, that was because that's what the software was expecting, is when you define counterclockwise, that is anything you don't want to draw in that particular case. And we initially mixed that up, which was a simple fix and was easy to fix.
And then we also had some challenges with the software library. The first one that took some time was just deciding how we wanted to return arrays of vertices and color attributes from our library, whether we wanted to pass it in by reference or return it from the functions. In the end, we decided to create get functions that you can see on the bottom of this slide. What's really cool about the get functions is then you can create multiple shapes and then get your vertex buffer and it'll have all the different shapes in there. Another challenge we had was rotating the 3D objects correctly. So we did not have a lot of success with MP3, so we couldn't even get a cube to rotate like it was supposed to with MP3. Also, we want to kind of have the rotation more inside the library. So we have this Euler angle YXZ, which creates a 4x4 matrix based on whatever rotation you want. And then what you have to do with this matrix is multiply all the vertices by this matrix and it will do the rotation for you.
So any idea what that Euler angle at YXZ does compared to, there's like a rotate function. I don't know the difference. I think they all create matrices as like the output, the view, model view. What does that one do specifically? What makes that?
So I don't know if this one does anything super special specifically, but I know when I was looking through all the functions in GLM for it, there were quite a few rotate ones where it would take either only the X or only the Y, only the Z, whereas this one will give you the full 4x4 matrix. It also allows us to, it's specific for the Euler angles. There's other ones for different angle ways that you could pass it in, like quaternions and whatnot. This is one that I just found to work.
It even just has a weird name, right? Like YXZ. So is it doing like, is it like yaw, pitch, and roll? Or I mean, it just
Yes,
the whole thing.
I'm pretty sure in the documentation that's how they think about it, is yaw, pitch, and roll.
Okay, then that okay. So okay. All right.
Then here's a picture of all our different tests for the different shapes. So we got squares, rectangles, triangles, circles, cubes, rectangular prisms, and pyramids. And all these examples do use face culling. Kind of hard to see with these examples, but they are doing it properly. And yeah, if you can tell on some of the objects, like with the cube, you have a red face. That's actually because we've turned it that far around where we're now looking at a different face. So that's pretty cool. And then
Can you
we can
explain
see
that? Can you explain that a bit more? That red face. So, because it's hard to tell, right? Is it a cube with a red face, or is it something that's being culled? Can you? Or is it just
so
that you've just rotated it?
we've just rotated it that far, and then yeah, face culling does its thing. So yeah, we just
Yeah,
turn
I
it
guess.
farther.
Yeah, to take it a step further, in our bottom middle image, you can see the two small cubes. They have a green top and then a dark blue left and a light blue right face.
Mhm.
So the red is actually the back face of the cube. So we ended up rotating it another 90-ish degrees. So we are looking at a different side of the cube. And this shows that even on the back of the cube, when you turn it to face you, the triangle rotation is still correct.
So I get that the rotation is correct, which is very cool and good to be able to show. But if you just had like depth testing working, wouldn't the result be the same, or can you actually tell that you've culling? Or this is just a demo of the software library, not a demo of the face.
Yeah, this is also more of a demo of the software library.
Oh, okay. So I was
Our-
thinking this was showing culling.
Yeah, it does have culling working, but if we go to the next slide, that specifically shows more of the culling working.
Okay.
Yeah, so on this slide, very basic demo application. It basically will cycle through the different options. So the first option we switch is what face we want to call, if we want switching between the front to back and back to front. And then we switch between what direction we want. So in the bottom in the console, you can see the different values being outputted. And then finally here, we can see that if you switch both values, you end up with whatever you originally had. So if you're calling the front face and the front face is counterclockwise, but you switch it to the back face and clockwise, the end result will be the same because you're just doing the exact opposite. And it doesn't look like the code is showing up here. It's hidden behind the image. But the idea behind it is you reset the buffers at the beginning. That sets up all our buffers for the software library. And then you call whatever shape you want. So this first one is like a shape pyramid. You pass the XYZ coordinates of the lower left point, and then you can pass width, height, length, and then the rotation in degrees. And then after that, you can add a color directly to it.
So far as our self-assessment, hardware, it renders appropriate. We were able to test it with having two different triangles, so we knew that worked. We didn't speed anything up for hardware-wise. Our software helper library, we got all the shapes we wanted, and then we also had some added circles, but that was the only one we could really justify that we had.
You added circles at 9:40 this morning. I know it counts. I mean,
Yeah.
So okay.
Yep. For our driver changes, we made an application that allowed to test everything that we made for this. And the report was very basic. We didn't have any of the math to show that we sped up because we didn't have any. You saw some of our report at the very first slide. So that's a very good example of what our rest of our report looks like. Yeah, any questions?
Yeah, questions for this team?
Looks like Matt has a question in
How
chat.
did you test
so-
for correct culling? Yeah.
Yeah, so I guess kind of for correct calling, most of the testing was visually looking at it because right off the bat, when it was run, we would see, oh, hey, this is the opposite of what we wanted. It's very much there's 4 states of what the calling could be in more or less, aside from enabled or disabled. So just comparing those, and then I guess I probably didn't make it completely clear in the face calling demo, but when it changes, what it's doing is it's switching from showing the outside or the front of the cube to showing the inside of the cube.
Yeah, part of the problem
that
is an
makes
optical illusion, right? Whether
Yeah,
is it,
yeah.
you can't entirely tell, is it a cube with all the faces or is it missing a face? It can look
Yeah,
very
it's
similar.
and that's like optical.
Optical, right. So anyway, I mean, so team, I think this was just great. I mean, so these projects were meant to be, MP5-ish, right? Of that type of scope, or even maybe a little bit less than that because you're kind of on your own and you're not getting direct support from me or from the TA in terms of figuring these things out. So you had a goal, you got it done, and it wasn't as much of a last minute grind. And I think that's you should feel good about what you accomplished there. Give a minute for everyone to fill out their assessments for this team. And then we're going to go to group 7 here in just a moment. And that'll be the last group for today. So we did pretty well on time. I had to cut a couple of you short, but I think we did great. And we're going to finish by that 11:45 deadline we have here. So when you submit for team 7 coming up here, make sure you page through to team number 8 and make sure then you may want to quickly review and make sure you have all your things in there. It's not the end of the world if you're missing a team, and you should be missing one for your own team. It's not the end of the world if you just didn't get something in for a group. It's fine. It's all averaged together. There's 31 students. It'll be just fine. But then make sure you submit. So for Qualtrics, I noticed you do have to hit submit for me to be able to just easily grab what you had for it. Couple more final notes I'll add after group number 7 goes here. So team 7, if you are ready to go, we can see your screen. Feel free to get started.
All right. So just a quick recap for what our team did is we tried to implement a clipping algorithm so that from a purely hardware side, you could just send everything to the board and then it'd clip or cull all the pixels that were outside the visible region. So for hardware, from just a high level standpoint, we ended up splitting that into a culling component, which would remove any complete triangles, and editing the current hardware to support clipping, where it would just cut off like partial triangles. And then from the software side, Ethan created a game. You chase down pieces of Suzanne to win, and you have ghosts chasing you along the way. So starting by diving a bit more into our hardware components, the culling algorithm itself was pretty simple, and we actually talked about it a little bit in class. Basically, what you do is you have, you split the screen up into 9 portions. And so, if it is above the top of the screen, then you assign basically it to be like a 1, 0. So if it's to the right, you assign the right to the 2 least significant bits to be 0, 1. And so altogether, you can use those to determine where each vertex is in a triangle. And so this component fits in between primitive assembly and then the triangle setup in the rasterizer. And so we just basically creating this new component, we go through a very simple set of if statements. Basically, if any vertex is equal to 0, 0, 0, 0, that means it's at least partially in, and so we just pass it on. If next we and all 3 of the vertices, and if there's a 1 in any position after anding them, that means it's completely off to one side, like here. And so that's just guaranteed out. Now, and then we get to the main edge case where if it's on a corner, it's pretty, it could be either in or out. So that requires a little bit more testing, which we'll dive into in a moment. And then otherwise, we just, based on the rest of our edge cases, we couldn't find any that would specifically be out. So we consider it in and pass it on. So to dive a bit more into that, here's the state machine diagram for the new culling component, which again fits right in between primitive assembly and triangle setup. And so we get the triangle in from primitive assembly. We go through that if statement that I talked about previously. Then if it's on a corner, we just, very similar to the rasterizer, where you check via the rotation of a specific point, whether or not it's in the triangle or not, we check a corner. So if it is located possibly or potentially on the corner of a of the visible screen, then what we do is we pick out that actual corner pixel, and then through these states, do that calculation for like C7, C8 to determine whether or not it is inside or outside of the triangle. And then if it's inside the triangle, that means the triangle is at least partially visible on the screen, and we pass it onwards. And if it's outside the triangle, then that means that it's not visible, and we cull the triangle.
All right, so now to kind of get into some of the software updates, we also featured Suzanne quite heavily. What a beautiful monkey. But we basically made a game. So we made a game based on the Bandersnatch series on Netflix, the single movie they made. And so basically it's a maze navigation game. So you've got 3D and free look controls. And then there's actually a whole bunch of physics going on in the background. You can collide with the walls. You can raycast to see if you're going to collide with an object you want to grab. And essentially the goal is to avoid the ghosts and, when it was implemented, the Bandersnatch as well. And so we implemented text rendering as well, as you can see down there in the lower image. We use text meshes to display text to the screen, and most of the ASCII characters are possible. I didn't want to spend all the time generating meshes for ones that weren't, but that's kind of where that laid. And then another one of our goals was also physical shading. This was the only one we just investigated and never really ended up implementing because it turned out to be a bit of a nightmare. So we'll move on and get into a little more detail here. So this is the game. This is the Bandersnatch game. As you can see, it's a pretty massive map. And basically, I spent a lot of time building up the engine to actually support something like this. So each mesh is actually loaded from an object file. It's just a collection of faces, and each face is just all 4 of our vertex attributes. And so each one of these meshes contains a whole bunch of data. It contains all those faces. It contains a base color, so you can color it however you want. And then it also has a transform. So it has its place in the world, and it's just a matrix 4, which we can actually manipulate at runtime. And so all of our rendering, because our vertex shader and isn't really working, we have it all going through a software rendering pipeline. So every single vertex is actually transformed before being sent to the GPU. All of our shading is done on the CPU as well. So basically we're transforming everything and sending it over to the GPU to just render pure triangles. So ideally this could run on MP2 hardware, which makes it a little less efficient, but that's okay. We implemented semi-garage shading. So it looks, you can see there up in the top, there is a light source and you can see shadows moving outward, but it's all software based. In addition, because we did text rendering, I also have an overlay layer. So basically you can have a HUD or some sort of stuff that is always visible on top of everything else being rendered. So that was mainly where we did our text rendering. And then there's also a whole bunch of utilities that kind of bundled in with this thing. So I implemented the Moeller-Trumbore algorithm, which is just a ray casting algorithm. So you can do mesh on mesh collisions effectively. You can see if one mesh is intersecting with another one, and if it is, you can trigger some sort of collision event.
And I'll put
And
one
then also-
final props for the real-time rendering book. And I don't know how many of you actually wound up getting it or grabbing it from the library or buying a copy. That's the same Moeller of the raycasting algorithm. So it's a very, it would be, if we had a 580, it would be the textbook for a 580 style of class. So you mentioned the name, so I thought I'd one final pitch for that book. It wasn't required for this class. It's a pretty good guide for advanced rendering techniques and real-time rendering optimizations in general.
It is a really good book, and there's some nice PDFs online if you want to take a look before you buy it.
It's
So
on Canvas. I put it on Canvas.
Is it on Canvas?
Yeah,
Okay.
so if you just want to grab it, that's fine.
It's okay. That's good to know. But yeah, so that's the end of our utilities stuff. So then next slide, Nolan. So this is a quick video of what the game looks like. You can see we have text rendering in the top left, and we're actually moving around this maze freely. And so I think I collide with a wall, hopefully at some point here, to show you that works. Okay, maybe I didn't. That's nice. Oh yeah, there we go. See, I'm hitting the wall. We're doing perspective division. We had a whole bunch of issues with our W component being weird. And so there's a bit of like distortion going on when you get close to stuff. I'm still not sure what I did wrong there, but generally it's working as intended. I uploaded the wrong GIF as well, so that's okay. There's pickups that are littered around the maze randomly. We use like, I think it's the Newth Shuffle or the Fisher Yates Shuffle to place stuff around the map. And then you actually go and collect them. And when you have all 5 collected, you win. So, and there's X's up in the top. Oh, this is the same GIF. There's the scary ghost that glides towards you through walls. Definitely not because I was too lazy to implement pathfinding. And so there we go. I'm going in to grab the pickup, and you can see I have an X because I picked one of them up. And yay, there we go. That's your short little demo of the game. And so text rendering, just quickly, we use text meshes instead of textures, mainly because textures don't work on our hardware. And it was just more likely people would have textures not working and triangles working. And so meshes also, if we're going to be very particular about it, you can use meshes in a 3D world. You can place them anywhere. And they look neater, I think, when you stretch them and widen them out on the screen. So all I did was I went to Blender, generated a mesh for every letter I wanted. Everything is in monospace font, so it's easy to place. And basically, it's just a whole bunch of object files that we're loading in dynamically and displaying to the screen. And this also takes advantage of that mesh class we created for everything else. This is a totally random example of text rendering. Please act surprised, Reed. Yeah, woo! Anyway.
Well, now I'm curious, is his name R-E-E-D or R-E-I-D? Because here in Zoom, it's R-E-E-D, but in Discord and here it's R-E-I-D. Yes, okay, that's what I was wondering. Yes, okay.
Oh, no. Oh, no.
No, you got it. I'm pretty sure you got it right. He has his own name spelled wrong here.
We're being gaslit.
I think so.
Okay, so now kind of getting back into the hardware. We definitely had some bugs as we were trying to implement. Culling, surprisingly, we implemented pretty smoothly, but we then tried to implement clipping to go along with the culling. So if triangles were partially on screen, we wanted to just not rasterize the part that was off screen. So change our triangle traversal algorithm to just ignore anything that's outside the bounding box and limit our bounding box to the edges of the screen instead of just being the outer bounds of the triangle. That was more difficult than we expected, and we were getting some weird behavior anytime we tried to tweak the triangle traversal algorithm to implement that. Here we turned our triangle into a half Christmas tree, half triangle. We kind of ran into this on the late side, so we didn't have enough time to really dive into this problem. So we just kind of scratched that style of clipping, and we'll see on the next slide. We attempted to take a roundabout, but I wanted to talk about the second bug first. So clamping, we were, I believe here, Ethan, if you wanted to dive into this, we were, as we would have an object roll off the screen, we would overflow into the other buffers because we weren't, we weren't being careful with the edges of our screen buffer as we were manipulating objects here.
And I think a lot of this too, like this was a software bug where I was set something up wrong with my perspective matrix, or I'm not copying a value over. And so I was getting negative W coordinates, which was just blowing things up. So I didn't really fix it. I just clamped it and it made it better. But yeah, I still haven't found the root of that.
Okay, so this was our roundabout to get around the clipping. We moved it past the triangle traversal and just put it in render output. We said anything outside of a predefined screen size, just ignore that vertex. So we attempted to do this. We had a build running last night. I think we started it about midnight or so. And we ran into this just super in-depth bug that was not a copy paste error at all. We were ignoring any vertex that was on the screen instead of outside the screen. We just nice greater than less than mistake. And when we had a blank screen, which makes sense then, nothing was being shown. So we flipped that and had a build running, but didn't really have it in time here to So
It's not too late to go check it right now. I mean, if you want to, you got one final build. Okay.
So our final results, as you can see with that bottom left one, those lines and triangles I didn't paint are a nice representation of the test script we were running. The lines are the bounding box, and you can see that those triangles are outside and are not being put on the screen. The same cannot be said for the top one, where they're on the line and peeking through, but they're still drawing on the other side of the bounding box. So we didn't get that fully working. In the bottom right, you can see the horror that is the game running on the board. Things are being rendered, but it is so incredibly slow. It is just making a mess. So like in the very top right, you can see a fully rendered skull, and the ghost does exist. Things are being rendered, and it's rendering somewhat properly. It's just, you know, Lovecraftian horror. So for our rubric, we figured we should get about 55 on the demo and report, about 65 on hardware completion, and 90 on software completion. Software completion, because we had text rendering, because we had a lot of functionality with the game, even if it didn't run perfectly on the board, the software was still very functional. Hardware completion, we got culling working, clipping was broken, so we felt we deserved points for how we set up the bounding box, how many bugs we went through, how we actually got it to ignore triangles that were entirely off the screen. We just had issues with the edge cases where they were half on, half off. And we felt our demo and rubric were sufficient enough for 55.
Awesome. Questions for group 7 here? So, okay, if you go back to the previous screen, Lovecraftian horror is fine. What do you think is the kind of so I understand not getting clipping the way entirely you would want it to work would cause all sorts of issues, I would imagine. What do you think, if you were to take a guess, what would you think would be the primary driver of this?
So part of it is I don't think we manually set our frame rate. We never got like the forced waiting, like the polling to wait until everything is done. So there are definitely triangles missing there. I think another part of it is that something might not be right with our multiple drive calls or with our multiple draw calls. So it looks to me like if you look at some of those like idols or skulls floating there, it looks to me like it's starting on the wrong vertices and kind of drawing triangles like at an offset almost.
So it could just be the triangle strip again, or triangle fan just off by 1, and that causing all sorts of...
And making it look like garbage, yeah, because it's not, yeah, there's no specific order to it. But yeah, you can see that some of the things that maybe have like some sort of weird, like every third object or something might be drawn correctly or some weird...
And I'm just thinking, you know, for future teams working on future projects, and I think it'll be a common project people would want to get working. So ignoring the performance issues and knowing that you'll have to render a frame and then wait a second or 15 seconds, that's one separate issue. What would be the best way to scaffold up a game in terms of testing on the board? And it could be, you know, maybe it's, you know, if you're not really confident in getting Flex Seal working, just as an example, don't try to get a game working. Something like that may be a good benchmark to have hit as a team. I mean, I think you did great. It's a really cool game, and you know, you implement a lot of things in hardware that weren't previously there. But I'm just trying to think for future guidance for teams. What can I tell them when they want to get Minecraft or a new game working or other things? What would be a good milestone to have hit first before you do that? And I think that's something I need to consider. Any other questions for Group 7? This is correct. Quake, not Doom, but yes. And in the previous iteration of the class, we were able to, and I have videos of that actually working in practice. So we have definitely added some real inefficiencies to our version of the infrastructure this semester. Part of that is resolution. We were doing 640 by 480 in the old version of the class, and so that's just that's your factor of 4 right there. Part of it is the rasterizer is a lot less efficient than the previous one was, but I think it's more straightforward. And then the shaders are really slowing things down as well. And so otherwise, I'm not entirely sure. And you could and teams could have tried that, by the way. So there was nothing stopping you from just rendering to a much smaller viewport and effectively doing 640 by 480 testing of things if performance was your primary concern. Um, that would be something that team 4 you could absolutely try pretty quickly, I would think, and see just with a smaller viewport, do we get 4x the is it render output bound, or is it vertex shading, or where the bounds are, and you can analyze that from there. Anyway, team 7, you can end your screen share here. You don't have to, but you can end your screen share here if you choose to. And I just want to make sure that everyone has filled out their surveys, and you should have gotten to a submit screen. And then if you've gotten to that, and then it says, thank you for completing this survey, that means you've done your job. I'll review all those results sometime tonight, and then I'll also start to take my look. But so I want Canvas submissions by this evening would be ideal. So if everyone needs to crash and sleep and you want to do it tomorrow morning, that's also fine. But relatively soon here, so I can get grading done. It's also fine by me. There's a lot of different codes and different ways to package it up. If you'd like to just add me to your repository, as opposed to trying to upload everything into a perfect zip file, that's also perfectly fine. Just mention that somewhere in your submission that, hey, we're just uploading a PDF, and in terms of code, you now have access to our GitHub or GitLab repository for it. That's fine as well, because I would like to look at certainly a few of your implementations at that point. So if you got to the very final next button, that would have submitted it. So if you go back to the last team 8, and hit the arrow button to the right, that would submit it. So we should have those in there. Otherwise, get some well-deserved rest, package that all together as best you can, get it written up and submitted. And I'll take my time with evaluating them and kind of averaging the scores together. It'll be interesting to see what your peers think about your project as well. Oftentimes we have these rubrics, but the scoring tends to be just kind of an overall quality impression. No matter how detailed the rubric is, people have kind of a snap judgment of, oh, they did a good job, or this was not as good as it could have been, and the score is then adjusted accordingly. We tend to be pretty generous to each other, and we've been generous all semester long, and I don't expect that to change. So you shouldn't be worried about your grade in this class, and I don't think anyone is. Otherwise, hey, it's been fun. It's been a bit of an experiment. It's been a little weird, and I actually really enjoyed it. I'll be seeing people on other side of August, hopefully, and otherwise, I'll keep the Discord going. We don't need to keep ours going, but when I start the next one for next spring, I'll invite you all back to that if you'd like to join. And if nothing else, you can heckle the students who are struggling with getting rasterizing working next spring, or you can help them. One or the other would be fine. Otherwise, thank you everyone, and I'll see you all soon.
Thank you.